Bismillahirrahmanirrahim. Assalamu alaikum dear students. I'm Arif and I welcome you all to the next session on the subject of system programming with Linux. The title of today's session is Process Heap Behind the Curtain. Well, today first of all we are going to have a quick recap of allocating, using and freeing memory on heap. Then we will dig out details about the layout of heap and heap allocators. We will talk about the BRK and the sbrk system calls. We will discuss common programming errors that developers do while handling heap. And finally, I will talk about different tools and libraries for malloc debugging. Let us have a quick recap of allocating, using and freeing memory on heap first. If you are new to using heap in C language, I strongly recommend that you should first watch lecture 9 of C refresher video series on the topic of dynamic programming, and then you should fall back to this session. Well, we know about process logical address space, and in the last session we discussed in detail as to how the process user stack is laid out and how it automatically grows and shrinks when function activation records or frames are pushed and popped respectively. Well, in today's session, we are going to discuss about the layout and working of heap, which starts just above the data segment and moved up till the memory map region. Well, dear students, the two main flavors of heap allocators that you come across are explicit allocators and implicit allocators. All the C programs use explicit heap allocators, as the programmer needs to explicitly free any allocated blocks which he or she has allocated using either the malloc or the new operator. On the contrary, Java programs use an implicit heap allocator, as it is the responsibility of the heap manager to detect as to when an allocated block is no longer used by the program and free the block implicitly. Well, this slide shows the malloc family of functions used to allocate and free memory space on heap for implicit as well as for user-defined data types. Dear students, in C, if a programmer wants to resize an already allocated block, he or she can use the realloc function, whose variant is not available in C++. Do read the man pages of these functions that you have time and practice how to use them. Well, over here I'm going to give you an illustration of how a 1D array on heap is laid out and how it is freed. The point to note before I proceed is that the program break, that is the BRK, in the beginning is pointing just above the data section. And of course, we all know that unlike stack, heap grows upwards towards the higher addresses. Well, when a C program, execute this line of code, it is actually a request to allocate memory inside heap for 10 characters, that is 10 bytes. Malloc function on success will return the starting address of that memory, and after typecasting it to a character pointer, it is assigned to a character pointer str. Remember, this name variable str over here will be created on stack, and it will contain the address of the unnamed memory on heap. You can see str has been created on the stack and it is pointing to the unnamed memory on the heap, and the BRK has moved up. Let me do it again. You can see how memory will be allocated over here and the BRK will move up. So this is how the address space will look like after successful execution of this line of code. Another point to note that BRK has not moved up just 10 bytes, rather has moved up to some multiples of system page size. Well, after successful allocation, we use this memory. And finally, once we are done using it, we call the free function. And when this line of code gets executed, the memory gets free, like this. However, note that the free function does not lower the program break. It is still there. However, it adds the block of memory which has been allocated, that is the 10 bytes, to the free pool of blocks that can be used by future calls to malloc. Moreover, the pointer variable str over here still exists on the stack. And we of course know that it will be automatically freed when the function that has declared this variable goes out of scope. Let us extend the same illustration and see how to allocate and free a 2D memory on heap. Suppose in a program we want to input 4 names from user, and each name can have suppose maximum of 11 characters, and both these values can be decided at runtime. So when this line of code gets successfully executed, an abstract pictorial view of the memory is something like this. So names is a stack variable of type character pointer pointer, which points to an unnamed memory on heap containing a 1D array of character pointers. Now, when this loop gets executed, actually we are requesting more memory on the heap. Memory on the heap for storing 12 characters, and this line will be executed for 4 times. Once for this, once for this, once for this, and once for this. When this loop runs for the first time with I is equal to 0, this much memory, 12 bytes of memory will be allocated, and the starting address will be returned to this location, that is name sub 0. And when this loop runs for the second time with I is equal to 1, the starting address of next 1D array is stored in name sub 1. And this process goes on for the third as well as for the fourth time. So finally we have the memory allocated. So now we use it. Suppose I put some names in it. Arif, Hadid, Mujahid and Yashar. Before I proceed, let me discuss a limitation of this approach. Suppose to cater for long names, the programmer has kept the size of each array as 100 bytes. So this array, suppose, is of 100 bytes. All these 4 arrays are of 100 bytes each. And the user has entered all names of, suppose, 10 characters each. So that means 400 bytes minus 10, 10, 10, 10, 40 bytes, almost 360 bytes of memories goes wasted. Well, you can try your programming skills to write down code that will allocate only that much amount of memory as per the number of characters entered by the user for each name. And I think I have discussed this in my C refresher course as well. Anyways, let's move ahead and see how we can free this memory. So we have a loop over here which runs, of course, 4 times, and every time it frees one of this array. So when this get executed with I is equal to 0, this portion of the memory on heap gets freed. When it gets executed for I is equal to 1, we have the second array freed from the memory, and then the third, and then finally the fourth. However, you can still see the memory or the 1D array of character pointers is still there on heap, and to free that we need to call free again with free subnames, and when this line gets executed, the entire heap memory is freed. But however, the variable names is still there on stack, and of course we don't need to worry about it as it will be freed automatically. Okay, so let's move on to the slides and see a program heap filler which will answer a question, a $100 question, and that is, if a process continuously call malloc without calling free, what happens and why? So let me cat this program first, heapfiller.c. In this code you can see I am entering in an infinite loop and continuously calling malloc for 1 MB of memory on heap. This memset function is actually initializing the allocated memory with null byte, and finally I'm printing a statement that says I have successfully allocated this much memory for the first time, second time, third time, and so on. So this loop will continuously run until memory for the heap is over. Let me compile this program and let me run it. It is allocating 1 MB blocks, and you can see it is moving ahead, and finally it will stop, and it has stopped at 3622. So system has successfully allocated almost 3622 megabytes to this process on heap before the call fails and the process gets killed. Let me make a minor change in the program. Heap filler. Let me just comment this line. Save and exit. Compile it again and run it. You can see this time we have crossed the previous limit of about 3600, a little over 3600 megabytes. What is happening? How come the heap has grown up to this extent now? But of course it will fill out very soon. But this time it has allocated a little over 623,000 MBs. So what has happened? Okay, the program in the second run actually was just allocating the memory and not using it. It was just allocating the memory. And since it was not allocating it, so this is the optimistic memory allocation scheme of the Linux operating system. That is, it deferred the page allocation. In simpler words, you can say that allocation doesn't actually happen until you really use that memory by writing data to that block. So due to this optimistic memory allocation scheme of Linux operating system, we have been able to allocate much more memory as compared to the previous run. Let us move back onto the slides and try to dig out a bit deeper to understand the working of heap. Well, this is the actual system called BRK. The resizing of heap is actually telling the kernel to adjust the process program break, and the BRK is a system call that sets the program break to the location specified by the address over here, and the upper limit to which the program break can be set depends on factors like the process resource limit for the size of the data segment and the location of memory mappings and shared memory segment above the heap. So once the heap crossed the area of memory mapped region, it gives the error and kill the process. sbrk is another C library wrapper that is implemented on the top of BRK. It is simpler as it increments the program break by this much number of bytes, and on success it returns a white pointer that points to the end of the heap before sbrk was called. I will be using sbrk and passing it 0 to get the current setting of the program break, and of course it will not change the BRK. Do see the main pages of these two calls, and let me move on to an example, brk.c, which will answer a query, and that is, after a process calls malloc, which in turn calls brk, what is the new location of the program break? Let me move over here and show you the program brk.c. Well, this program first of all prints the location of the program break by calling sbrk sub 0. Then it uses malloc to allocate 100 bytes and prints the address which it has returned. Then it again calls malloc and prints the program break, and then again malloc and prints the location of program break, and then again malloc and prints the location of the program break. So assumingly, after each time we call malloc, the position of program break should change, but we will see this is not the case, as I have said before. Well, you see, this was the initial location of the program break before I call the malloc function, and once the malloc is called for the first time, it has moved to this address. Before we called, the address was 756,000, and after the first call it became 777,000 hex. So the first request was just of 100 bytes, but the program break moved up to this address, almost little over 100 kilobytes. And after the second request and the third request and the fourth request, the program break remains at the same location. So this is what I have said a while ago, that once you request memory on heap using malloc, the program break jumps quite up with some multiple of the page size and not just 200 bytes. Let us move on to our slides again and try to do some scuba diving to understand the details. Let me now describe how a basic heap allocator works. This diagram shows a horizontal view of heap when a program starts executing. You can note the BRK and the end. They both point to almost the same location. On the first call to malloc, the program break moves ahead, some multiple of page size ahead, providing you a contiguous memory allocation area to play with. Now within this area, the program keeps on allocating and freeing chunks of memory. So after some time, we have some allocated blocks and some free blocks within this area. Well, this is the structure of an allocated block on heap, which consists of two parts. Over here, we have the length of the block, and then this is the memory that is available for use by the programmer. And remember, once you call malloc, malloc returns this address and not this address. Similarly, this is the structure of a free block. Well, the free blocks in this area are managed as a doubly linked list. And a free block contains first the length of this free block, a pointer to the previous free block, a pointer to the next free block, and then the remaining bytes of the free block. Let us move ahead. Okay. Now this slide gives you a clear picture. This shows the state of the heap after a process has made calls to malloc and free. You can see there are two allocated blocks shown in yellow and three free blocks shown in green. A process can access the allocated block by the address returned by the malloc function. And you can also see that every free block has a size of that free block shown over here, and the pointer to the previous free block, which points to the previous free block, and a pointer to the next free block, and then we have the remaining memory of the free block. Whenever a process requests for memory on heap using malloc, the heap allocator scans this entire list, this free block, then this free block, then this free block, and so on. And it assigns the memory as per some contiguous memory allocation algorithm like nextfit. And if no block on the free list is large enough, only then malloc will call sbrk to move it further ahead and allocate you more memory. Hope this concept is quite clear to you. Most of the heap allocators manage their heap using this scheme. Now another $100 question is, when a process calls free, how does it know as to how much memory it needs to free? Does it has any effect on the program break? Well, remember, when you call malloc, the address returned is, suppose, this one, and you call free on this address, and the 8 bytes immediately before this address contains the size of this block. And this is the value with which the free is called. And this is how free comes to know that how much memory it needs to free, and makes this allocated block a free block later on. And the answer to the second question is, does it have any effect on the program break? Well, of course not. It does not have any effect on the program break. It just put this allocated block to the list of free blocks. And once you free this block, and if there is a block which is free before this block, or if there is a block which is free after this block, the blocks are merged together to make a bigger chunk of memory. This is called coalescing free chunks of memory. Okay, now the question is, why not use BRK or sbrk? Well, always prefer using malloc family of functions to allocate and deallocate memory because they are standardized part of C language. They are easier to use in threaded programs, and they provide comparatively simple interface. Well, why free doesn't lower the program break, rather adds the block of memory to a list of free blocks to be used by future calls to malloc? The reason of this is the block of memory being freed is somewhere in the middle of the heap rather than at the end. So the lowering of program break is not possible. And the second reason is it minimizes the number of sbrk calls that the program must perform. Okay, let's again move on to the terminal and see a piece of code that makes our concept more clearer. Allocated block.c. Well, this program receives a command line argument, converts it to an integer, and then requests that much number of bytes on heap for 1, 2, 3, and 4 times. And finally prints the address is returned by malloc. Let me do gcc allocated block.c and let me run it with a value of 1. You can note that I have requested just 1 byte on memory. So the difference between this address and this address should be 1. But you can see the difference is of almost 20 hex or 32 bytes in decimal. So the question is, I requested 1 byte and the system has given me 32 bytes instead. And the same behavior goes on up till I give an input of 24. So even if I asked 1 byte or if I asked 24 bytes, the system is giving me 32 bytes. Let me clear screen. The system has hanged up. Okay. Let me cat again. And now let me run it with 25. So once I run it with a request of 25 bytes on heap 4 times, the system is giving me 30 hex. After 10 I have 40, then I have 70, then I have A0. The system is giving me 30 hex or 48 bytes. The same pattern goes on up till I request for 40 bytes. And if I request for 41 bytes, you can see now it is giving me 40 hex or 64 bytes. And the same pattern goes on up till I request for 56 bytes. So what is this? Let's move back. So $100 question again. When a process requests 1 byte or up to 24 bytes on heap, why the memory allocated is 32 bytes? And when a process requires 25 to 40 bytes on heap, why the memory allocated is 48 bytes? And when a process requires 41 to 56 bytes on heap, why the memory allocated is 64 bytes, and the same pattern goes on. I hope that you should be able to answer this question. If not, you can leave a comment on the comment box, or you can email me after trying something. Let me move ahead. Well, this slide shows the 5 common programming errors that most programmers do when dealing with heap. You must not do these. The first is trying to read or write freed memory areas. The second is reading or writing memory addresses before or after the allocated memory using maybe faulty pointer arithmetic. The third is freeing the same piece of allocated memory more than once. The fourth is freeing heap memory by a pointer that was not obtained by a call to malloc package. And the last is memory leaks, that is not freeing memory and just keep allocating it. Let us move on to the terminal again and see a buggy program. Let me clear screen. Let me show you the code first. Hello bug.c. Okay. So this is a simple program. I am requesting for 10 bytes, and in case of error, I'm just printing a message and returning the error number to the parent. Over here, I'm using it. I'm printing. I'm freeing, and I'm returning. Let us compile and run this program. And it executes successfully. It gives no warnings and no errors. And I'm sure you must have seen some error in this or bug in this program. Let me use splint program, secure programming lint. It is a tool for statically checking C programs. Its older version is lint, that is used to analyze source code and flag programming errors and bugs. If it is not installed on your system, you can install it using apt-get install. Let me pass hellobug.c to this program, and you see it gives you one code warning, and the warning is memory is used after it has been released. At line number 17 over here, you can see that we are freeing the memory, and after that we are using it. Let me try to correct this program. hellobug.c. Let me just comment this line, and let me call splint again on hellobug.c, and you see this has finished checking without any warning. So dear students, please make it your habit to statically check your programs for common programming mistakes using the splint tool, the secure programming lint tool. Let us move back onto the slides. Well, there are certain tools and libraries as well that you can use for malloc debugging. And the one I'm going to use today are Lec10 and Valgrind. And let us check the same program, hellobug.c, and this time let's use the Lec10 library to find out the bug. Let's move on to the terminal. Let me create the bug again by uncommenting this line. Let me do gcc hellobug.c ./a.out. So it's successfully compiled and executed without any warning or error. However, it will of course give you an error at a very wrong time once the software will be deployed. Let me link this program with the electric fence library. If you have not installed the electric fence library, you can install it with sudo apt-get install electric fence. So this is the latest version. I have already installed the latest version, so no problem. Do see the man page EFENCE. Do read it at the time of your ease. Right now, let me link this hellobug.c with the libefence library, and let me use -g gdb option to add the debugging symbols as well. So if I run, it gives you segmentation fault now. You have seen previously it runs successfully. Now it is telling me that there is some problem with this, and the problem has been identified because of the electric fence library. Let me do an ls over here and see if a code file has been generated due to segmentation fault or not. Well, no code file is generated. Let me use ulimit-c and make it to unlimited, and let me run it again, and this time you will see a code file will be generated. You can see this is the code file which has been generated. Well, a code dump is a file that contains the memory image of the process at the time of its termination. It is generated normally in case of abnormal termination. Now let me load this code file in GDB and investigate the reason of termination of this process. So it has loaded it and it has given me the problem. The exact line is 18, where I'm assigning this character to ARR 0, and that is after it has been freed. You can see this is the line which has given me the error. Well, now you know about electric fence. Let me move back and let me talk about the Valgrind as well. A Valgrind is a suite of command line tools that are used for debugging and profiling. And let me try a faulty program and check out the bugs in this program with Valgrind. If you have not installed Valgrind, you can install it using apt-get install Valgrind. Do see the man page of Valgrind. I have already installed it, so it is there on my system. And let me show you the program, faultyprogram.c. Well, this is a long program. Let me use the first function, that is f1, and if you see this function, there is a bug in this program. Actually, over here, instead of a comparison operator, the programmer has mistakenly used an assignment operator. So this if-else structure will always be evaluated to true, and as per the logic, the line that should be printed is variable number do not contain 3, but it will print variable number contains 3. This is a very common programming error. Okay. So an easy solution to identify such programming bugs is to always compile your program with the -val option. -val with a capital W. If you compile with this, it will give you maximum possible warnings, and the warning is, it is telling you that you should have used a comparison operator over here. Okay, fine, let me comment this line and let me see what I have in function 2. Okay. Well, inside function 2, you can see I'm requesting for 10 bytes of memory on heap by malloc, and over here I'm using ptr sub 13. I'm trying to access memory location ahead of the memory that is allocated to me. Let's check this out. And you see there are no warnings, no errors, and the program executed successfully. This is a very small program, that's why it has been executed successfully. If it would have been a large program and a program that runs for a longer time, you might get into serious problems. So let us check this with Valgrind. Once I run it with Valgrind, it says over here invalid write of size 1, and over here the error summary says 1 errors from 1 context. Let me clear screen. Let me do Vim faulty program again, and you know how to correct this error. I leave it on to you. And let me enable function 3 and let's see what's the bug in function 3. Okay, can you tell me? Well, yes, over here we are trying to write a memory location after freeing it. Let me do gcc faulty program.c and let me execute it. And this time it gives a segmentation violation. And unfortunately, whenever your program do a segmentation violation, it doesn't give you the line number on which the problem is there. So better is to load the file, the code dump file which it has created into the GDB, or you can use Valgrind and check out what the problem is. And over here again it says invalid write of size 1, and trying to write inside a block of size 10 freed. You can see this line. It tells you what is the actual reason of the error. Let me clear screen again. And let me vim faulty program. And let me move on to the function 4 now. Let me comment this line. And let me move on to function 4. And inside function 4, you are seeing that we are freeing the memory twice, which is again an error. Let me do gcc faulty program.c and let me run it. And you see this time again it has code dumped by giving the errors on std out as well. Let me use Valgrind for this. Okay. So this time it says in the heap summary, if you note, it says 1 allocation and 2 frees. And by seeing this, you can come to know that we have used free twice while we have requested malloc once. Let me clear screen again. Let me vim faulty program.c again, and let's see what we have in function 5. Okay. Well, in function 5, you can see we are not freeing the memory at all. We have requested the memory, we have used it over here, and then we are just saying bye-bye. We are not freeing it. That means gcc faultyprog.c.a.out. It works fine. If I use Valgrind on this program, it once again says the leak summary. We have lost 10 bytes in one block. Okay. Let me vim faulty program again. Well, you might be thinking that these are very simple bugs, but dear students, these are just 4 to 5 lines of code. If the bug is there in a huge program that is spread into multiple files and written by multiple developers, it will be a nightmare to locate such problems. Okay, let me see this function now. Function F5. Okay. No, we are going to talk about function 6 now. Okay, function F6 is calling a function getString1, and well, this getString1 function is creating an array, a string of characters on its stack and returning that address to function F6, and function F6 is printing it. Once you will run this program, it will compile without any error and it will run without any error. This is because we are immediately accessing the contents at this address ABC. However, if in between these two lines, that is where I have called getString1 and I have printed this ABC, if I am calling some other functions in between them, and then I am accessing the contents of the stack at address ABC, we might get garbage as output of this printf function statement. This is because this has been created on the function stack frame of getString1, and I am trying to access the function stack frame of getString1 in the function stack frame of F6, which is of course an error, and this is what we have seen in our previous session as well. And the correct way of doing it is shown in over here in the function getString2, and in getString2 we are allocating the memory on heap for this purpose, and later on in function F7 we are accessing this memory, and this is the memory on heap now. And this is one of the advantage of using heap memory, and that is it is available across the function calls because it doesn't exist on stack. Let me move back onto the slides again, and I hope we are done now. Okay, that is all for today's session, dear students. Hope it was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. Wish you all the best. Happy learning, and Allah Hafiz.